All right, let's get this party started. So welcome to the HVAC game, our electrical troubleshooting live webinar. And thanks for taking the time to be here on this Saturday morning. It's very good to see you. I really love having you. So let's get into this. So first, how to make the most of this, some points to consider to get the most value from this webinar. Obviously, we're all here to learn. We're all here to improve ourselves and share knowledge. Then please be courteous to each other in the chat or whatever you're asking questions in the end. If you have questions, then raise your hand or post in the chat or just keep note of it. We are going to end this with a Q&A. So if you have questions, just take note of it. And then in the end, we're going to give you the opportunity to take those up. Lastly, if you want a copy of this presentation, you don't have to take screenshots of everything or take notes. I can just send them to you so you can either reach out to me in the community or just email info@thehvacdane.com. In the beginning, let's do some legalities because obviously this is a presentation for certified trade professionals or people getting into the trades. As the HVAC game LLC is not liable for accidents, injuries, damages resulting from the application or information provided in this webinar. It is, I have a general liability waiver here. You can read through this. You are the technician on site, so you will obviously always know better than me because conditions change, safeties change, state laws are different. So just be aware of your local laws and everything. Just take a moment and read through this. Just type in the chat done when you're done. It's just that you as a technician are responsible for your own safety, that you're taking care of yourself, and that this information is for informational purposes to help you as a technician get trained. Awesome. Okay, let's move on. Let's get into our troubleshooting. What we are learning today, first of all, we're going to go over electrical basics because to do electrical troubleshooting, you will need to understand the basics. So we're going to go in what is electricity. We're going to cover voltage, amperage, and resistance. After that, we're going to go into troubleshooting electrical issues, and I have it divided into several sections of how I troubleshoot and diagnose. Lastly, we're going to have a Q&A. And in the end, I have a little bonus slide that you can take with you for reading electrical wiring diagrams. First of all, why should you listen to me? Well, you should always listen to yourself because you are the technician in the field. You are on site. You will have the equipment right in front of you. So if there's something that I say in here that doesn't make sense in the specific scenario, then obviously listen to yourself. But since you're here, you probably have seen some of my content. You're part of the community. So you know about what I do, what I share, and you know that I never assume that I know everything. I'm always learning. And what I'm sharing here is what I have learned since being in the trades since 2011 and just what has worked for me. What makes me uniquely qualified to deliver this webinar on electrical troubleshooting is that actually before I got into HVAC, I did an apprenticeship under a licensed electrical contractor. So that gives me a different perspective because he really taught me electrical basics. Also, for the first 3 years of my HVAC career, while I was a building engineer, I did not have my EPA license, which means I was unable to connect my gauges to the system. And all the troubleshooting I did was based on electrical diagnostics, control boards, and measuring because I could not hook up my gauges. So I could only see if the system was low based on pressure switches and stuff like that. So that just gives me a very unique perspective on electrical troubleshooting. And it gave me a focus more on electrical troubleshooting than other stuff. So what is electricity? Electricity is basically the flow of electrical power or charge. And it is a type of energy that can build up in one place or it can move from one place to another. So that is static electricity is when it stays in one place. And you can think of it like, I don't know how many of you have done that as a child, take a balloon and rub it against your hair. You're building up this electricity. Your hair is kind of like attracted to the balloon, but you don't have the transfer of electricity. Versus if you plug your extension cord into an outlet to run your vacuum pump, for example, you have the electricity flowing through your electrical, like your extension cord. Electricity is basically a potential of energy. And the way you can think of this is in your outlet, you have the hot side and you have the neutral. If you don't plug anything into the outlet, nothing happens. So you have the potential for work being performed there, but nothing happens. Now, if you plug in your vacuum pump, your heat gun, your hair dryer, whatever you want to plug in, now you're getting the flow of electricity. You're having the work that is being performed by using that electricity. Voltage is the word that we use to describe that potential of electrical power. It basically tells us the difference of electrical potential that we have from one place to another. That is the voltage. You can think of it like a running water pump, but the valves being closed. So this is a nice big pump here. And just imagine you have this pump running, but over here our valves are closed. So you have the pressure, you have the potential for the movement, but since your valves are closed, you're not going to have any work that is being done. That is voltage. You're just having the difference between the pressure that's there and something that could have happened, but that isn't done yet. Here, this is obviously an outlet. It's probably a European outlet because we're measuring 240, but you have your hot side and your neutral side. Nothing is plugged in, which is why we're having this voltage differential here. Now, what is amperage? Basically, once you open the valves, like in the analogy of the pump, you suddenly get the flow of water, of electricity in this case. But the flow of electricity that you have now moved, that's performing some work. Once you measure that, that is your amperage. You can think of it like a little trickle versus a large amount of water. So you have like a little bit of amperage, a little bit of electricity moving, or a lot of it. How you could think of this is, let's say you have a heating stage or you have two heating stages on your equipment. You have one stage engaged, so you're pulling whatever you're pulling, 10 amps, 15 amps. Now, when your second stage comes on, you're pulling double of that because now you have a lot more electricity flowing through that equipment and your amperage is going up. So that's little versus a lot. You have different scenarios where that happens, like train, they have two-stage compressors where the first stage pulls a certain amount of amps, the second stage comes on, you pull more. So those are ways you can think about this. The way to measure it, you take your amp meter, you put it around your wire. Obviously, only take one because you don't want to connect it to your hot and your neutral because then you're not getting a reading. If you're taking two wires, you're getting a reading that's probably going to be incorrect. So always take one wire, measure it. That will give you a certain reading. Lastly, we're going to go into resistance. And what is resistance? Basically, as electricity pushes through any physical object, that object will have some form of resistance. Now, there's resistance is the opposition to the flow of electricity in an electric circuit or component and is measured in ohms. Now, there are some materials that are considered conductors, which means it's easy for electricity to flow through. And there are some materials that are considered insulators, which means it's hard for the electricity to go through. Glass, for example, is a very good insulator. Air is a very good insulator. Copper, on the other hand, aluminum, they're considered conductors because electricity flows through them easily. But even if you have, for example, copper on a coil, there is still inherent resistance. As you can see on a contactor, you have the coil. When you put your meter on it and you measure resistance, you still get like 5, 8, 10, 12, 15 ohms, whatever you're measuring. So there's always some form of resistance to your electricity, which is here. All electric components will have a certain amount of resistance. And each circuit needs resistance to function properly, which is something that some people don't think of. But if you have your coil on the contactor, for example, go below the specified resistance, you will have a short and then your system will trip. The way to measure your resistance is you put your meter on ohms, obviously turn your power off because you don't want to be measuring resistance with your power on. You put one prong on one side of the component or whatever you want to measure. If you want to measure from line to ground, for example, on your compressors, put it on one side and then the other on the other side or to ground, and you get a reading. That is what you see. So that concludes the first section. That was very quick, just overviews. I hope that all makes sense. I just keep checking the waiting room to see if people's joined, but it doesn't look like it. So, all right, so let's get into troubleshooting. The first thing to think about and to keep in mind is that there is a precise way to troubleshoot electrical problems, and it's not just, okay, hit or miss, or I'm guessing. So there is a precise way how you can go about it. In electrical troubleshooting, the thing that you're looking for is you're trying to find out where the flow of electricity stops, where the electricity takes the wrong path. Oh, I thought there was a third one. Okay, so it's where the electricity stops or where the electricity takes the wrong path. And the three main points that I think of when I troubleshoot for electrical problems is one, either an open line, which means that you're reading OL, there's an infinity of resistance, there's no connection. Two, there's a ground fault, which means there's an unintended connection to ground. Or a short circuit, which means there's an unintended connection to another wire. And many of you might think that a ground fault and a short circuit is kind of the same thing. And you're correct in that a ground fault is a form of a short because a short is an unintentional connection anywhere, and the ground fault is just a specialized type of short. The reason why I separate them in here is because each of those gives you a separate set of identifying factors that help you to trace down, and they also have a different appearance in the system and they cause different things. That's why I separate ground fault and short circuit in here. First of all, let's talk about open line, which is OL. OL basically means that there is an open circuit or infinite resistance. It also means there is no current flowing through the measured area, and it indicates that you have a broken connection or a faulty component. As I covered earlier, air is a very good insulator. As you see here on our meter, it is set to resistance. You're reading OL, you have your prongs here, your leads. They're not connected, there's air in between, which means there is no connection, there is an infinite amount of resistance, so you won't get any flow of electricity. That's why it's reading open line. How would you go about finding that problem? First of all, I would check for power, because if you have an open line, you will probably not have power at your equipment. You check your data tag to find out what the voltage is supposed to be. Sometimes you get weird voltage readings, and you want to make sure that you're checking what you're getting based on the data tag. You can either check from terminal to terminal or from terminal to ground, and you're getting different voltage readings based on that. Depending if you're working in commercial or residential, if you're checking from terminal to terminal, you'll probably get 208 to 30, or if you're working on 460 equipment, you might be getting 460. In residential, you're probably going to get 240. If you're checking from terminal to ground, you're probably going to get 120, 118, depending what you're getting on the line voltage. But that's what you're checking for. Then you would narrow down where your system is breaking down, where your open line is. Here we are checking fuses. We're having the power on the equipment. It's always safer to turn the power off and check with resistance. But this is just here to show you that it is possible to check bad fuses with the voltage. So down here, it's a little bit small, but you can see it's on voltage. We're having 0 volts. And if you remember, as we covered in the beginning of the webinar, voltage is a potential difference. So you have a potential of electricity. Here, we're checking for a bad fuse. We're getting 0, which means I covered all of these. If you're reading 0, it means that your fuse is good because you're having the same voltage potential on both of the sides of the fuse. If your fuse is bad, as you see in the next slide, we're just going through all of these fuses and we're checking them to make sure they're good. Down here, This was actually a 460 equipment. So here we're reading 460 because the power is coming in on one side of the fuse, but it's not exiting on the other side of the fuse, which means the fuse is bad. And now you have the potential difference here, which tells you that the fuse is bad. This is another example of an open line where we had a bad fuse. This is with the power off. Here you have your equipment set to resistance. You're measuring the fuse, it's reading open line. As you can see, this was our culprit. Very sad early demise of this lizard. But this lizard got behind the fuses. It made an unintentional connection between these two fuses. It blew one of the fuses. Obviously, the equipment wasn't running at that point, but we removed that. We replaced the fuse and the equipment was running. Let's get into ground faults, which is the next one that I'm talking about. A ground fault is a situation where an electrical current accidentally flows to the ground instead of following its intended path. This is often due to damaged insulation or a faulty connection or a bad component. One thing to keep in mind specifically on a ground is that the ground is a safety device. It is connected to your equipment. It is connected to all of your conduits. It is supposed to be connected to the electrical panel, and it is a safety feature for you. If you think about not having a ground, for example, if you would have line voltage accidentally touch the side of the equipment and there's no connection to ground, the entire equipment would be hot. So if you would be touching the equipment, you would then become the connection to ground. The electricity would flow through, which means that you would get shocked. The ground is there to open a very low resistance path to ground, which increases the amperage that is being pulled on that circuit, which then either blows the fuse or trips the breaker. So it is a safety device. It is a safety feature. So keep that in mind when you're installing equipment. Always make sure that you have a good ground. How to find the problem if you're having a ground fault? First of all, I would separate high voltage from low voltage and see where your problem is. If you don't have line voltage present to the equipment, you can be fairly certain that your breaker is tripped, your fuse is blown, there's something going on the line side, and you do not need to worry about your low voltage at that point. On the other hand, if you have your line voltage present, but you don't have your 24 volts control voltage, there's probably something going on the low side where there's some kind of short there. So just ignore the high side for now and just focus on your troubleshooting on the low side. So you can separate that, break down your equipment. One thing to remember is don't just reset. Breakers and fuses are safety devices. They usually trip for a reason. So if you just reset it, you might just be replacing the fuse, resetting the breaker over and over until you actually find the problem. As you can see over here, this is a low voltage transformer. The fuse is tripped. You would obviously look for the cause first and handle that before you move on. Resolving the issue includes you turning off the equipment. Then you put your meter on resistance, like down here. I mean, here you can see we're reading 642 ohms resistance, but you're tracing the problem and you're measuring to ground because you're looking for a ground fault. So you're checking either your wires to ground, which means your line, like L1, L2, L3, if you're working on three-phase equipment, or two phases, you're taking one line and you're measuring to ground. Or you can take your individual components and measure the components to ground. That would be like something that you do if, for example, you suspect that your compressor is bad, you remove the plug and you put your leads on the compressor and then to ground. So that's how you check your component. So between those two, you're separating high voltage from low voltage, and you're checking either line to ground or the components to ground. You can break down the system, the entire AC unit, the whatever, like split system, whatever you're working on, into like little chunks that you can easier like identify and break down. If you are checking for bad components, for example, you can isolate the component. Let's say you have a heat strip where the heat kit is broken and there's an unintentional connection to ground. So you go through, you check after the contactor connected to the heat strip, you check to ground. You see, okay, which of the heating elements is broken. I'm talking that's obviously about larger commercial units. On residential, you might just have one, so it's very easy to identify. But the same goes to compressors. You can check your compressor to ground, the individual legs in the compressor, your condenser fans, your heat strips, blower motors. You can do each one of those isolated, check to ground. That way you find your component. I personally like the way of checking your individual lines to ground. That is probably because I work a lot on three-phase equipment. And on three-phase equipment, you usually have some components that are single phase. You have three-phase compressors, for example, and then single-phase condenser fans. That is just as an example. But I would, for example, check L1 to ground, and let's say it's reading OL like it's supposed to be. Line 2 to ground, it's reading OL. Line 3 to ground, and now we're getting a connection there. It's reading like 0.5 ohms, whatever you're getting. There's some kind of connection. You're not supposed to have any connection there. So now I know, okay, this is the component must be on line 3, like L3. If I, for example, know that my condenser fans are only on line 1 and line 2 because they're single stage, they're single phase, I know that I can exclude those from my diagnosis and I don't have to worry about them right now. So then I can just narrow down. That just helps me personally narrow it down faster. Okay, I hope that makes sense. If you have questions, take note of them. We'll take them up later. So let's get into the short circuit. A short circuit is when an electric current flows down the wrong or unintended path with little to no resistance. Electricity follows a different path than its initial design, and it can cause serious damage. Now, to recap, the reason why I separate the short circuit from the ground fault is because of one main reason, and that is on your low voltage side. A short circuit can be a connection between two wires that not intentionally trips the breaker. But the example that I like to use is, let's say you have a heating coil, your W1 terminal, and your insulation on the white wire is broken. It is making an unintentional connection to your Y1, your yellow wire. Now your system would be running in heating and cooling at the same time, which causes system inefficiency. You will get a call, either a no heat or a no cool call because your system is inefficient, but your breakers would not necessarily trip. Your low voltage might not necessarily trip. So that is a short circuit that causes a problem that will lead to a service call that is different from a ground fault. And yeah, as you remember, in a ground fault, usually you would have a fuse blow or something go wrong. You will probably not have power to the equipment. So that's why I'm just separating the two out. How to go about finding your problem? Honestly, the easiest is visually or by smell. Usually on a short circuit, you will see melted black wires or you will smell something burnt in the equipment. In this case, we opened the control panel. The contactor was obviously, I mean, all you see the wires there, but there was an immediate smell of burnt wires, and it was very easy to isolate here. But you could also have like sparks inside the equipment, or you could have a mechanical component failure, or the breaker might be tripped. That's not always the case, but it can happen. How to go about resolving the issue? Well, obviously, first, ensure the power is off. Always make sure you're safe. Then you narrow down the source. As you can see here, we had the power off. This was during a preventative maintenance. I don't know if you can see it, but there's sparks coming out of the motor down here. We turned on the power. The motor was shorted internally. We turned on, but it sparked and smoked and stuff like that, so we turned it off right away. So we turned off the power and then we verified the component is actually the component that has failed. Here we turned it on resistance. We checked the motor internal windings. It is reading 246 ohms, which is way higher than it's supposed to be, because if you go back to this picture, You can see it shorted out. Usually a spark like this creates heat, it melts wires. Now, when you're trying to read resistance on the component, you will get a higher resistance than usual because your internal windings are short. So then you would go replace components, because usually on a short circuit, you will have to replace components. And the way to do this, so you isolate your component that's failed, then you verify that it is the component. And in a short circuit, usually you will have to replace the component. In a ground fault, sometimes it happens that a wire just rubs out and the breaker trips. You can replace a section of the wire. You don't necessarily need to replace components in that case, and you can have the customer up and running. One trick to keep in mind here is if you have multi-stage units, you might be able to, as you see in this example here where we replaced the contactor, you might be able to just take out that contactor. If this is your second stage cooling, you might be able to disable the second stage while you're getting a component. If the compressor burned out, for example, in this case, disconnect stage 2, have the customer run on one stage, so at least they have partial cooling. That is just something to keep in mind as you're doing service calls. You might be able to get the customer up and running in that case. Now let's go into a specific note on low voltage, because low voltage shorts can be harder to trace, mainly because they're harder to locate visually, and sometimes you do not get burnt smells or burnt marks. The way to identify it is by knowing that you have line voltage present, but your control voltage is not there. In this scenario, specifically over here, we were doing a PM and we noticed that the condenser was not running. So we went to the air handler unit and we noticed there was no control voltage present. We then obviously turned off the power with it. We usually do that, turn off power. Then we took our meter, we put it on resistance. We checked terminal to common. So we would go R to C. We would check what our resistance was. It was good. Then we checked our, W1, G, Y1. We check all of them to common. In this specific scenario, we had on Y1 to common, we were reading 1.5 ohms, which is very low. The only thing that you would be reading on that is probably your contactor. So here, next picture, you can see this is on the condenser. This is our contactor. Now what you would do is you have your coil here, this and this. You just put your leads on it like so, and you check what you get as resistance. And obviously here we're reading 1.5. So that's how we trace the low voltage problem in this specific scenario. One thing that I could advise you to do is test resistance on new components that you're installing. I used to do that quite frequently. I don't do that as much anymore, but specifically on contactors like this, I like to know what the resistance is on the coil from the manufacturer. I would used to think that it's around, well, what I saw mostly was 7 to 15 ohms resistance as good. If it got below 7, I would get suspicious. But recently, I've encountered contactors that read 5.8 ohms on the coil coming from the manufacturer. I installed them and they're still working. So just make sure that if you have a problem on an equipment and you find a contactor that is reading low resistance on your coil, replace it, continue your troubleshooting. Okay, this is already the main part. This is the end of the main part of the presentation. Obviously, my main point is for you to stay safe, be certain in your ability to troubleshoot with the power off, but there's only one of you. So always make sure that you're wearing PPE, that you stay safe, that you troubleshoot with the power off. And yes, you're the most important. So I hope this presentation helped you. It clarified some of the stuff. It gave you some more ideas on how to troubleshoot. And now I would like to go into Q&As. If you had any questions, you can put it in the chat or you can raise your hand and then you can ask your question. Yes, sir.
Uh, I wanted to piggyback off of when you were speaking on low voltage. Um,
Yes.
I had a scenario where I encountered with low voltage, and low voltage is very, or on the residential side, low voltage is very tedious, um, really tedious. But I saw that you're at the AHR conference,
Mm-hmm.
um, and the Jumper King. I've known that to be very helpful in certain situations when you got like low voltage issues. And then another component is called a free stat. I mean, a zebra stat. That is like basically the component becomes the thermostat, and it has on there where it'll allow you to see which wire or terminal, you know what I'm saying, is showing where the short is. So
Mm,
um,
okay.
I just wanted to, let everybody know about that and make that investment. If you didn't want, to have time to ohm everything out, those components can help you out. The Jumper King, I think it's like $60 or
Yeah,
it's
it's
not
60,
expensive.
$70. Yeah.
Yeah, the zebra stat is it's about $200. So
Yeah. Okay. I've heard about the zebra stat, but I haven't really seen it. But yeah, I have the Jumper King.
mhm.
I use it in certain scenarios, but yeah, it can be very good in helping you find shorts in the circuit. Yeah. Especially if you have to climb like in the attic and go between your
Yeah,
air handler and the condenser and you're like
yeah.
trying to
Uh,
go up and down ladders. So
Yeah. So I haven't got one yet, but I'm in a process of getting one.
nice.
Because the Zebra stat is a little, like I said, it's about $200. It's a little bit more expensive, but they do the same thing. But I know the Jumper King it has other features as well, other than the low voltage situation. But I just wanted to piggyback off of that. Just let everybody know, those devices that can help you, yeah, be more efficient on calls.
That's awesome. I appreciate that. Thanks, Ivan.
Yeah.
Okay, any other questions? You can put it in the chat or just raise your hand. Okay, well, if you have something, I'm gonna give one last tip before we go. If you think of something, just put it in the chat. But one tip I want to leave you with in terms of troubleshooting in general is know the sequence of operation of your equipment. It sounds very fundamental, and part of that is also read the manual. In the beginning, I know, at least for me, manuals were very daunting and I didn't really want to read them. But every manual has a sequence of operation. It's usually a page or two out of the manual. So you just go on the front, just go on sequence of operation, just go on that page specifically. Get familiar with the sequence of operation of your equipment. Because if you don't know what the steps are that the equipment takes to provide cooling to your customer, it is very hard for you to troubleshoot. An example of that is having your safeties, let's say your overflow safety switch on your secondary pan installed. Sometimes it is installed on the 24 volts control voltage. Most of the time it is installed that way, but sometimes I've seen it installed to just cut out the cooling to the unit. That would mean if you don't know how the system is thinking, and you have 24 volts present, your fan is coming on, your cooling is supposed to come on, but your compressor is not starting, and you are not aware of the fact that you have a safety switch installed in line with with the Y1, you would miss that point, and it might be very hard for you to trace it down. That's why it's so important that you understand how the system operates and how the system thinks. And that gets even more important when you get into, for example, refrigeration, especially low temperature refrigeration, where there is a lot of controls. There is defrost time clocks, there is other sensors that cut out the compressor. And usually manufacturers are very good about giving you the sequence of operation in the manual. So just, take the extra minute, find that on the manual, just read the page or two. It's usually not more than 2 pages that I found. And it's very good and it makes sense. Usually sequence of operation is very logical. An analogy I could give you, it's like, you have all of these checkpoints. So if you want to go on the trip, for example, you have the intention of going on a vacation, and then you have to check your bag, you have to go through TSA, you have to go board the plane, you have to give your boarding pass. They're checking everything. So these are all these different little checkpoints. So you have the idea to your like dream vacation. In terms of HVAC, you have the idea of a comfortable space for the customer and the outcome of, hot or cold, depending what the customer wants. And from the start of that idea, you have all of the different checkpoints in between. Those are your safeties, your high pressure, your low pressure, your overflow safeties, your condensate might be clogged. There's a lot of different things that tell the unit what is going on with the unit. You might have some outside temperature, like outside air temperatures for the unit that turn on or off cooling and like lower temperature zones. So these are things to think about. And that's just my little advice to you in the end of this. Go through sequence of operation, learn what the system is supposed to do, and just start getting familiar with manuals by reading that little section because it's very digestible. You can read through that in a minute or two. And that's just a little tip I wanted to leave you with. Hmm. That's a good question. Um, Matthew is asking about a website or app to look up manuals. I usually just Google it. I know the Blue On app used to be good, but recently it's become paid, so I don't know exactly if you can look it up there. I know if you go on Parts Town, they sometimes have manuals for equipment. Otherwise, usually the manufacturers nowadays, they all have apps. I know like Train has an app. I don't know if they keep because you're specifically asking about 17-year-old units. I guess it's supposed to say trains.
Yes, sir.
Okay. Autocorrect sucks.
Yeah.
Does it all the time.
Oh, yeah. I just now see it. Yeah. 17-year-old chance. That's it. Not a good look for me. Um, but yeah, so we're the old R22 train systems.
Yeah.
And when I pulled them out to do my first check-in, like uh to check capacitors and everything, looked at where the manual should be on the inside of that little panel we remove.
Hmm.
Nothing was there. So it was like, okay, well, there's probably, I could probably just Google the model number. Well, 17-year-old equipment's kind of hard to find info on. So I was just seeing if there's like an archive or something available for like if I do run into that again.
Yeah, there is. I have to find the website. I can probably post it in the community later. I think it's
Okay.
like manualslib.com or something like that. I find a lot of manuals on there.
Okay.
It's like you can click through the manual. Sometimes I've also had it where I call tech support and they're able to email older manuals to me.
Mhm.
But yeah, that's a good point. Like, let me look around and see what I can find. But I usually Google it, but
Mhm.
specifically on older train units, yeah, I've had problems getting manuals sometimes. So let me see what I can find and I'll post it
Yes,
in
sir.
the community.
Thank you.
Sure. Okay, so that is the end for today. Thank you for attending again. I really appreciate you taking the time on Saturday and going out of your way and learning more about your trade, about your chosen profession. That is very, very good of you. And no, it's not. Oh, here. I want to show you the last slide. Hmm. It's all blank. Is it blank for you too? It's loading. Let me
Yeah,
see.
yeah, I can't see anything on my end.
Let me see. Ah, there we go. Okay, so that's the last one I wanted to leave you with. If you want to, you can take a screenshot of this specific page, but I just put some common symbols on electrical wiring diagrams that you will encounter. So you can take that with you because it will help you to trace circuits and trace wiring diagrams. You have resistance up here. These are your coils, for example, on contactors. These are fuses, capacitors. This is just a general symbol for ohms for resistance. This is usually your symbol for transformer. Contacts on your contactors, normally closed, normally open. And then this is your pressure switches, high pressure, low pressure. And then this is a temperature sensor, and these are usually high temp cutouts and low temp cutouts. The way to identify these is usually if they're high pressure, they're closed, and when the pressure goes up, they open, and the other way around like this. So it just hopefully helps you to navigate electrical wire diagrams. I wanted to give that to you. And that's the end of the presentation for you for today. And again, it's awesome that you took the time to be here. I appreciate it. I hope you learned something. And yeah, I'll see you next time in the community. Have a good day. Have a good weekend.
Appreciate it. I appreciate it, Sasha.
Yeah, you got it, man.
This I just wanted to let you know, I'm still new to the trade as well as in the field. But what you have with the HVAC game, I want to give you your flowers now. This is for me been very helpful. That you took your time out to, out of your busy day, and you doing your service calls, that you've made this. So I really, really appreciate this. I've introduced to some of my classmates and people that I know. Just taking advantage of investing into the trade, into their craft. So what you have here, I really like it. I really appreciate you doing this, man.
Oh man, I love it. It makes me feel so good. Thank you. I'm glad it can help you. That's awesome. That's why I do it. And yeah, thank you. I wish you were like in Texas, because not the next week, but in 2 weeks from now, we're gonna have the meetup in
Yeah, I saw that.
north of San Antonio.
I can come see you. Meet you. Hopefully one day, man, I can come out to Texas and person.
Yeah, I mean, honestly, like my long-term goal for the community is also to host more in-person like workshops. That's really what I would love to do, like workshops, and then maybe have like areas. You're from Atlanta, no?
Yeah, I'm in Atlanta, Georgia. Yeah.
Yeah, okay. So yeah, it would be cool like if we have a bunch of people like over there, maybe you and some of your buddies or something.
Right.
Then we can organize. You're like, okay, we would like to learn that, and then I don't know how we're gonna finance it, but it would be cool to just spend a day or a weekend or whatever you want to do, and just meet up in person and say, okay, we want to learn about refrigeration, or we want to learn how to braze, or specifically control boards, or something. So that would be really awesome. Anyway.
Yeah. Hopefully, because I'm here for the long haul. So hopefully,
Yeah, me too. Me too.
can get together in person, and that would really be great. That definitely would.
Awesome. Thanks. I really appreciate it.
Oh, no problem. And whenever you in the near future, I know I was telling you about the shirts.
Yes.
I definitely will want to. Whenever you make it to the community can buy, I definitely want to get one.
Yeah, I want to make them so I like them myself, but
yeah,
I don't like the white one. I mean, if you like it, I can buy some and send them to you.
Well, the white one, I'm gonna be honest, I'm not really good with white.
Yeah, exactly. I don't like it.
Yeah, so it's like the black would probably be more my preference. But yeah, whenever you decide to do that, I definitely want to get one.
Awesome. I'll let you know.
Okay, I appreciate it, man.
Thank you for the kind words. I appreciate it. Enjoy your weekend, man. Have a good weekend.
You too. All right, see you guys later, man.
Yeah, see you. Bye.